Every day, millions of people chat with ChatGPT, Gemini, DeepSeek, Claude, and other AI assistants. Behind all of them is the same core technology, large language model, or LM for short. You ask a question like, "What is AI?" And within moments, the large language model responds with a thoughtful, coherent answer. But have you ever wondered what actually happens inside? Let's find out. When we look inside, we find a fascinating pipeline. And in just 5 steps, you'll see exactly how large language models understand your input and generate responses. Steps 1 through 4 handle text understanding, making sense of the input. Step 5 handles text generation, producing the responses. And the transformer sits right at the heart, powering both. Now let's explore each of these steps in detail. Step 1. Text to token. The model splits your raw text into small pieces called tokens, words, subwords, or characters that it can process. It all starts with the raw text you type in. For example, the words "Hello AI." But a model can't read words the way we do. It needs to break them down into pieces it can work with. This process is called tokenization. The input text is split into individual tokens, in this case, hello and AI. Each token is then assigned a unique number, a token ID. Think of it as a lookup number in a giant dictionary. These token IDs are what the model actually works with from this point forward. The raw text has been converted into numbers the model can process. But an ID is just a lookup number. It doesn't capture what a word means. That's where step 2, token embedding, comes in. Each token is mapped to a high-dimensional vector, a list of numbers that captures its meaning and relationships with other words. Let's take our first token, hello, with ID 42. The model looks up this token in an embedding table and retrieves a vector, a long list of numbers. This vector has 384 dimensions, meaning it's a list of 384 numbers. Each number captures a different aspect of the word's meaning. The same thing happens for AI token with ID 137. It gets its own unique 384-dimensional vector, a completely different set of numbers that represents what AI means to the model. Each of these vectors is a point in a high-dimensional space. We can think of it as having 384 separate axes, far more than we can visualize directly. So let's project this down to just 2 dimensions to make it easier to understand. Here in 2D, we can see where hello and AI land as points in space. Each word occupies a specific position based on the numbers in its vector. But what do these positions actually mean? That's what we'll explore next. These vectors don't just float in isolation. They live in a geometric space where words with similar meanings sit close together, enabling the model to compare and reason about them. Now let's see how the model captures meaning through the positions of these vectors. Here, we have a simplified 2D view. Remember, the real space has 384 dimensions. Let's plot some words. First, hello, at, and right nearby, hi. These two are greetings. They mean almost the same thing. Now, AI, and close to it, robot. Both are technology concepts, and way down here, car. An unrelated word far from the others. Notice the distances. Hello and hi are only 0.20 apart, very close. AI and robot are just 0.35 apart. Small distance means similar meanings. The model has learned that these words are related by placing them near each other in vector space. Now look at hello and car. They're 2.15 apart, a much larger distance. Large distance means different meanings. The model knows these words have nothing in common. This is the key insight. Distance in vector space equals semantic similarity. The closer two words are, the more related their meanings. Words naturally form clusters, greetings like hello and hi group together. Technology concepts like AI and robot form their own cluster. So when the model sees hello AI, it understands this as a greeting combined with a technology concept, simply by looking at where these vectors sit in space. Now the model knows what each word means, but it still doesn't understand how they work together within a sentence. That's the job of step 4, the transformer. The transformer is the brain of LLM. It uses self-attention, feed-forward networks, layer normalization, and residual connections. all working together to deeply understand and process the text. That sounds complex, but don't worry, we'll break down each component in detail. First, let's get an overview of the full transformer architecture. On the left, we have input processing. The input text goes through an embedding layer, then positional encoding is added, followed by dropout for regularization. In the center are the transformer layers, a stack of repeated blocks. Each block refines the model's understanding of the text. Here, we're showing 3 blocks, but in practice, there can be many more. On the right is the output head, a layer norm, then a linear layer, then softmax, which produces the final prediction. Let's watch the data flow through. The sentence, "the cat sat on the," enters the pipeline. It gets tokenized into individual tokens, each one flowing through every stage of the architecture. The tokens travel through embedding, positional encoding, dropout, then through each transformer block, and finally through the output head, where the model predicts the next word, mat. Now let's zoom into positional encoding, how the transformer learns about word order. Here's the problem. If we shuffle the words in a sentence, the embeddings stay the same, but the meaning changes completely. The cat sat on the mat, and mat the on sat cat the use the same words but mean very different things. The solution? Give each position a unique signal, a positional encoding. Think of it like a barcode. Each position gets its own unique pattern. These patterns are generated using sine and cosine waves at different frequencies. Fast waves change quickly between neighboring positions, capturing local patterns. Slow waves change gradually, capturing long-range structure. Here's a heat map of the positional encoding values. Each row represents a position, and each column a dimension. Notice how every row has a unique pattern. No 2 positions look the same. To put it all together, the model takes the word embedding, which tells it what the word is, and adds the positional encoding, which tells it where the word is. The result is a final embedding that knows both what and where. Positional encoding adds word order information using sine and cosine waves, a simple but powerful idea. Next up, dropout, how the transformer prevents overfitting. Overfitting is when a model memorizes the training data instead of learning general patterns. Some neurons become overspecialized, and the model fails on new data. Transformers are especially vulnerable because they have massive numbers of parameters, often hundreds of millions. Attention mechanisms can overfocus on the same tokens, and repeated layers can compound errors. The solution is surprisingly simple. During training, randomly turn off a percentage of neurons, typically 10 to 30%. Each training step drops different neurons. This forces the network to be robust. No single neuron can dominate. The model learns distributed, redundant representations. During inference, when the model is actually answering your questions, all neurons are active, but their outputs are scaled down to compensate for the ones that were dropped during training. Why does this work? Think of it like training a team by benching the star players. Everyone else has to step up. You end up with a stronger, more versatile team. In the transformer, dropout appears in 3 key places: after embeddings, after self-attention, and after the feed-forward network. Each placement regularizes a different part of the model. Now, let's look inside the core component, the transformer block, the repeating unit that powers the entire model. Starting from the bottom, input embeddings flow in. First, they pass through multi-head self-attention, where each word learns from every other word. Then through dropout, then add and normalize. Next comes the feed-forward network, 2 linear layers with a ReLU activation in between. It expands the representation, transforms it, then shrinks it back. Another dropout and add and normalize follow. Notice these yellow arcs on the side. These are residual connections. They carry the original signal directly past each sublayer. This prevents information loss and lets gradients flow smoothly during training. Think of them as information highways. In practice, multiple blocks are stacked. Early blocks learn surface patterns and syntax. Middle blocks capture relationships and grammar. Later blocks develop deep meaning and reasoning. Each block builds on the understanding developed by the one before it. Now, let's dive into the most important mechanism in transformer blocks, self-attention, how each token learns from every other token. Consider the sentence, "The bank of the river was steep." What does bank mean here? It could be a financial bank or a river bank. The word river in the same sentence tells us it's the riverbank. Words need context from other words to be understood. That's exactly what self-attention provides. Here's how it works. Take the word sat in the cat sat on the mat. Self-attention lets sat look at every other word and decide which ones matter most. It pays the most attention to cat, the subject, and mat, the location. To do this, the model uses three components: query, key, and value. Think of it like a library. The query is your question. What am I looking for? The key is the label on each book. What do I contain? And the value is the actual content of the book. Query and key together determine who to attend to. Value provides what information to pass forward. The attention scores are computed using the formula. Attention equals softmax of Q times K transpose divided by the square root of the key dimension times V. Let's see this in action. For the word sat, the attention scores might be cat gets 45%, mat gets 30%, and the remaining words share the rest. In the attention heat map, each row shows how much one word attends to every other word. Each row sums to 100%. Before self-attention, each token only knows about itself. After self-attention, each token is enriched with information from every relevant word in the sentence. Sate now knows about cat and mat. Finally, multi-head attention runs several attention mechanisms in parallel, each one specializing in a different type of relationship. One head might focus on grammar, another on meaning, another on proximity. Their outputs are combined for a richer understanding. Self-attention is how transformers understand relationships between tokens. But understanding alone isn't enough. Next, the LLM needs to produce a response. Finally, the model uses learned probabilities to predict the most likely next word and builds its response one token at a time. So far, we've seen how a large language model understands text through tokenization, embedding, and the transformer. But understanding is only half the story. How does the model actually generate the response? That's what we'll explore now. The key idea: the model generates one word at a time, each one chosen based on everything that came before it. Here's how it works. You ask a question: what is the capital of France? And it enters the pipeline: input, transformer, prediction. The model's first prediction is the, but it doesn't stop there. That output word feeds back into the input through a feedback loop. Now the model sees, what is the capital of France? The, and predicts capital. This process repeats. Capital feeds back in, the model predicts of, then France, then is, then Paris. Each word becomes input for predicting the next one. This is called autoregressive generation. But how does the model know when to stop? There are three stopping criteria. First, the EOS token. The model outputs a special end-of-sequence token, signaling it's done. This is the most common method. Second, a stop sequence, a developer-defined delimiter that triggers the model to stop. Third, a maximum length limit, a safety cap to prevent the model from generating forever. In practice, models combine multiple stopping criteria. But how does the model decide which word comes next? How does it choose Paris over Lyon or Berlin? Let's trace the full process. The context, the capital of France is, enters the transformer. As we saw earlier, it uses query, key, and value representations with self-attention to build a rich contextual understanding of the input. Now comes the crucial next step. The model scores every word in its vocabulary, all 50,000 or more of them. Each word gets a raw score called a logit. Paris might score 4.2, Lyon 1.8, Berlin 0.9, and dog -2.5. These raw scores are converted into probabilities using the softmax function. Softmax takes each score, raises e to that power, then divides by the sum of all such values. The result, Paris, gets 89% probability, Lyon gets 8%, and everything else gets much less. We can visualize this as a probability distribution, like a spinner, where each word takes up space proportional to its probability. Paris dominates the spinner. But how does the model sample from this distribution? There are several strategies. Greedy decoding simply picks the highest probability word every time. It's fast and deterministic, but can be repetitive. Temperature sampling adjusts the probability distribution. A low temperature, like 0.3, makes the distribution sharper, so the top word becomes even more dominant. A high temperature, like 2.0, flattens the distribution, giving more creative, diverse outputs. Temperature is like a creativity dial. Top K sampling only considers the K most likely words and ignores everything else. This eliminates unlikely, nonsensical choices. Top P sampling, also called nucleus sampling, includes words until their cumulative probability reaches a threshold, say 95%. This dynamically adjusts how many words to consider. In practice, models combine these strategies. For example, using temperature 0.7 with top P 0.95 to balance quality and creativity. And that's how a large language model generates text, one carefully chosen word at a time, drawing on everything it has learned about language. Now you know all 5 steps. Next time you chat with an AI, you'll know exactly what's happening behind the scenes.